first few. Okay, so on number 1, what should you have gotten? What should you have gotten for number 1? B. Any questions on that one? Everybody okay? Okay. All right, on number 3, you should have gotten what? E. On E, on 3? Okay. Can somebody talk me through 3?
So let's put that student even got five out of how many prizes? That would be 9%. So it's not unfair because it is a possible likelihood. It's just a very small likelihood.
Jasmine, you get it?
Yeah, I just can't see it. There's always
Super tiny. Yeah. Okay. That's okay. I should have blown that one up a little bit bigger. Okay. Number 5. B. Okay. Questions on that one? Okay. 7 part A. What'd you get?
Yes, 1.0.
Say again.
0.075 or 0.5%.
Anybody else get something else?
Oh, so, no, sorry.
0.10? Yeah. Okay. So you should have gotten 4 out of 40. And that would have given you 0.10, right? Okay, 5 was B. All right. For 7B, what'd you get? Do Kate's results provide convincing evidence of more than 20% of the upper class at her school use ChatGPT for schoolwork?
Yes. I don't know if like statistics would prove that overall. I don't think enough trials like we give a general just for this population because out of you would be looking at the 5 and above for those who that's the 20% that he's talking about. So out of 25 people, anyone who did anything 5 and above would count for that. So that would have to be from the simulated trials, about 55% would have more than 5. I just is 5 is good. That's 20%. I would think that. Like how many of the classmen are using ChatGPT? And ChatGPT is 20%.
So we had 0.1 in the last problem, right? Okay, 0.1, is it bigger than 0.05 or smaller than? Bigger than. Okay, so no, we don't have convincing evidence. Okay, so no, we don't have convincing evidence because the probability of getting a result greater than or equal to 8 purely by chance is 0.1, which is greater than 0.05. Okay.
Can you just say?
So the probability of getting a result greater than 8 purely by chance is 0.1, which is greater than 0.05.
We just did so you have to say greater than.
You have to kind of make that comparison of what did you get versus the 0.05. Because remember how we say like 5%.
So you have to
Okay. On 9A, what'd you get? Write this off to the side. 9A, what'd you get? Did we not get that far? All right, take like 1 minute, go over, look at 9. What's the first thing we're going to do when we have a two-way table? You add up the totals if they don't already give it to you, okay? So it's 110 for all of these people. Okay. So what's the probability that a person bikes to work? That's going to be 12 out of the 110. Man, more than a 30-minute bike ride. Oof. Okay. What is the probability that a person bikes to work and commutes at least 30 minutes? That's going to be 3 out of 10, 110. Good. Okay. And then what is are the events of a person biking to work and commuting at least 30 minutes mutually exclusive? So can they occur at the same time?
Yeah.
Okay, so since they can occur at the same time, no, they're not mutually exclusive. Okay. What is the probability that a person does not take a car to work? They're going to add up how many people do that. That's 30 out of the 110. Questions? Okay, put that to the side. Go ahead and take out your packet. Somebody remind me where we left off. I think it was part 4 on that pop quiz section. Okay. So on Thursday, man, I haven't seen y'all in a couple of days. Good Lord. Okay, so on Thursday we talked about how we can plug this into our calculator, and we did the whole binom PDF, right? And that was where we said N was the number of trials, P was the probability that it happened, and then X was the expected, like what we were actually looking for. Okay. So we were trying to find the probability of all of these. Yeah. Did y'all finish filling in the table? Okay. So some of you have, some of you haven't. Take like 30 seconds. Go ahead and knock that out. Okay. Yeah.
But I figured out a way to like.
That's right. You want to talk it through?
Yeah. So when you're going to enter the probability.
Okay.
Wait, I forgot how to get to the table. Or not the table, but to get to like.
Go to menu. Go to stats. Statistics. Oh, I'm sorry. Go to number 5, probability. So we go to menu, go to probability number 5. Okay. Now, depends on what you're looking at. The rest of it is up to you. It's probably going to be under distributions. Okay, under there is where the binomial PDF is. I always found a different way to do it where it calculates all of them all at the same time, so you don't have to do it for each individual one. Okay. So I'll share that with you in just a second. For 0, what'd you get? 0.237. For 1, you got 0.396. For 3, you got 0.088. For 4, you got 0.015. And for 5, we got 0.001. Yes, ma'am. Like how to find it. If you go into calculator on your calculator, okay, then you're gonna hit menu. Then you're gonna hit number 5, probability. And you're gonna hit distributions. And then you're gonna hit binomial PDF. And then you're going to put in whatever values you need. So for instance, on number 3, if we were finding it for 2 correct answers, then we would put 5 trials. The probability of successes would be 0.25. The expected value would be 2. You would hit OK. And then you would multiply it. Looking at number 3, we multiplied it by 0.25 raised to the 2nd power times 0.75 raised to the 3rd power. Yep. All right, go for it.
I know probabilities are
Okay.
distribution. They're binomial PDF. You input the number of trials, which is 5, and then the probability of success, which is 0.25, and you just leave X blank. And when you hit enter, it'll display all the values. You might have to scroll to the right, but it might be harder if there's like 10 or 20 because you have to scroll. So, but at least with the smaller table.
Okay, so if you don't put the X value is what he's saying, then it gives you all of the ones. Yeah. Questions? Okay. Alright, let's go ahead and look at number 5. It says calculate and interpret the mean of the distribution. So how would we find the mean of this guy? We would take our X value, multiply it by our probability, and add it to the next one. 1 plus times 0.396 plus 2 times 0.264 plus 3 times 0.088 plus 4 times 0.015 plus 5 times 0.001. When we plug that into our calculator, we're going to get 1.25. Okay, so the interpreting part is probably the tricky part, if you will. So with interpreting, remember, we have to say after how many trials? Many, many trials. Or many, many quizzes, because that's what we're actually talking about. Many, many quizzes. The average number correct is 1.25 questions in the long run. Okay, so what are the key words on this? Many, many. What else? Long run. Okay, so talking about the long run, saying after many, many, whatever context it's talking about. Okay, and then obviously stating the number. Just finish your recommended assignment. Okay, I'm gonna show you a shortcut. You don't have to do all of this jazz. Ready? So we can actually find the mean by taking the number of trials and multiplying it by the probability. So what were our number of trials for this one? 5. Okay. And then we had 0.25. So 5 times 0.25 gives us 1.25. Look at the up above. No, it was the probability of, because we had 4 choices, right? We had A, B, C, or D. So the likelihood of you getting it right would be right. Okay. Now for standard deviation, I'm going to go ahead and show you the equation for this one to make your life a little bit easier. This is going to be sigma equals, God bless, the square root of n times p times 1 minus p. N times p times 1 minus p. We're taking the square root of that. Okay, so go ahead and take a moment. Go ahead and plug that into your calculator and tell me what you get. What's good? Good thing you don't need your computer right now. Have you plugged it in?
No, it's not a battery. It just stays on this.
Okay, so take a moment. Go ahead and find the standard deviation. Okay, so you're gonna hit that refresh button and power off like multiple times. See if it resets it. You might have to do it like 5 times. All right, so what did you get for your standard deviation? What did you get for your standard deviation? I got 0.968. Yeah, okay. Nova's very cute. So she's like, oh. Okay, so what does this actually mean? This means that the number correct on a quiz typically varies by 0.968 questions from the mean of 1.25. So the number correct on a quiz typically varies by 0.968 questions from the mean 1.25. Keywords here, typically varies. And then you also want to state the mean. Obviously, put that into context. When we interpret something, you've got to use the context. We okay? Nothing too crazy. Okay, so I'm going to introduce something new on this next one. So, what is the probability of getting at most 3 correct? So, at most 3 correct. So, we're going to come down here. All right. So, probability of at most 3 correct. That means that we're going to add up 0.237, because that was for 0, right? 0.396, because that's for 1. 0.264 plus 0.088. And that's going to give us the probability of 0.985. Okay, so again, it says at most 3 correct. Now, let's say that we had 100 different variations of this, right? Like, let's say that, they had A through triple W as an answer choice, right? Okay, that would be way too long to add up all those options. So the way you do this in your calculator is if you want the probability of at most 3 correct, you're going to go in and do binomial CDF. And still type the same things in. 5 trials, probability is 0.25, and X would be whatever number you want at most. Okay, it's still in the same location. You go into menu, you go into probability, menu, probability, you go into distributions, but then you scroll down to binomial CDF. That's right under PDF.
It's just like the lowest we could get is 0 correct.
Right.
So then the lower
So the upper bound would be 3. Okay. All right, so what is the probability of getting 3 or more correct? Go ahead and take a moment. I want you to think about this one. We want 3 or more correct. How would we do that using our table? Just add them up. What are we going to add up?
0.088.
0.088.
0.015.
Okay.
0.001.
Okay. And that's going to give me 0.104. Now, if we wanted to do this using our binomial CDF. How would we do that? Okay. I also want to introduce this idea because I feel like you're going to see this notation as well. So don't freak out. So if I want x is greater than 3, you're going to have 1 minus the probability of x is less than or equal to 2. You could do it that way as well. Okay. So we could do 1 minus binomial CDF. CDF. Okay. And we would say n equals 5. P equals 0.25. And x would equal 2. Exact. We're going to use PDF. Okay. So if I get exactly 2 correct, I'm going to use PDF. If I want at most or more than, I'm going to use CDF. Just when you do more than or 3 or more, we had to do that 1 minus the CDF. Okay. Again, you're going to get comfortable with using these because you're going to use numbers that are bigger than like, hey, there's only like 5 trials. There's going to be like 100. Okay. All right, so let's recap. Flip the page. Yep. 0.25. Yeah. When I get down here, it gets a little iffy. All right, flip the page. All right, so let's recap. What did we learn? Okay, so when we want exact, so probability of x equals k, we're going to do binomial PDF. And we're going to put N, P, and K. When we want the probability of x is less than or equal to k, we're going to do binomial CDF. And we're still going to put the probability, we're going to put in probability and whatever x value we're looking at. We talked about the mean is the number of trials multiplied by the probability. We talked about the standard deviation, where that's the square root of NP times 1 minus P. And we also talked about how to interpret them. So with mean, after many, many trials, let's try this again. After many, many groups of N trials, average number of successes is whatever the mean is. For the standard deviation, we said the number of successes typically varies by whatever your standard deviation is from the mean, whatever your mu is. All right, so let's chat through it a little bit. All right, so on A, is it a binomial random variable? Yes. How do we know?
It's binary, there's 2 options, they're not.
Right.
Each trial is independent because it's third replacement. They did it 10 times, that's the fixed number, and then, yes, they were,
The probability.
yeah, it was the same probability as that.
Okay. So again, that's bins, right? Okay, that's how we memorize it. So success, you need to define the success and the failure. You need to state why it's independent, not just say, hey, it's independent. Okay, you say fixed trials, you say that the probability is 0.2, because it's the same probability every single time. Okay, the mean is 2. You would have gotten that by taking 10 trials and multiplying it by 0.2. Okay, how do we interpret this? What do we say?
Repetition of this experience. The average number of success would be 2, so, or would approach 2.
Okay, in the long run, right? The only thing is on this one, we want to say the number of trials. So we're going to say after many, many sets of 10 drawings. So we'll simulate that over and over and over again, okay? All right, for standard deviation, you should have gotten 1.26. How do we interpret that one?
Number of successful.
Go ahead. You got 1.6. Did you do this formula? The square root of NP times 1 minus P? Say again? You get the calculator, it's not the same number? Uh-huh.
Well, I just.
Okay, you got the same number? Okay. All right. For the interpretation, so we got the number of crinkled papers in a set of 10 typically varies by 1.26 from the mean of 2. Your paper is blank. Now chatting it up. Okay. Now, what's the probability of getting 5 or more? How would we go about doing this? Are we going to use binomial PDF or CDF?
Yes.
Remember, it's 5 or more. So are we going to use PDF or CDF? CDF. Okay, and so we are going to do 1 minus binomial CDF. And what we would plug in is we would say, how many trials? 10. That's probability 0.2. And then what number are we going to look for? We want 5 or more, so we want 4, right? So we do 1 minus everything below 5. Okay, so you should get 0.0328. All right, here's the tricky question. The student experiment resulted in 5 crinkled papers selected out of the 10 draws. Does this provide convincing evidence that the crinkling paper makes you more likely to win a random drawing? Is that 0.0328 less than 0.05?
Yeah.
So is it statistically significant? Yes. So yes, 0.0328 is less than 0.05. So the result is statistically significant. Good. Questions? Yep. D, we did 1 minus binomial CDF. What we're going to plug in for our CDF is 10 trials, 0.2 because the probability, and then 4 because we wanted 5 or more crinkled papers. So we found we found it for 4 and then said 1 minus 4. What's the lowest you could have gotten on that? If you put 0 for the lower bound and then 4 for the upper bound, because you can't have negative numbers, right? Right. So then you're going to do 1 minus 0.967, and that's going to give you 0.0328. Does that make sense? Okay. All right, go ahead and flip the page. And flip the page. Have y'all had green Skittles before?
No, never. I would love to try it.
And
Yeah, but apparently there's a green apple one and then there's like a lime flavored one.
Yeah, absolutely.
That's so sad. How'd you get 2 for the last one? For the mean, N times P. What are your number of trials times the probability? 0.2. And that gives you 2. What's the probability of getting a crinkled paper? 20 divided by 100. Yeah. Okay. All right. So in 2021, the Skittles changed the flavor of green from sour apple to lime. Gross. Mr. Wilcox tastes a small handful of 5 Skittles from a bin of 10,000 Skittles and gets all green. If 20% of the Skittles are green, what is the probability of this happening? So is this a binomial setting? Oh, are there success and failures? Okay. Is each thing independent? Are you putting back Skittles that just you put in your mouth? So it's not independent. Okay. All right. What about the number of trials? How many trials did we get? Okay. And then what about the probability?
Because it's not independent, like they're taking away a green skill or like a different color skill, so the probability.
Okay.
why does it not?
What do you mean, why does it matter?
Why did binary?
Oh, because you either have green apple or you don't, or you have lime or you don't. But you get 10,000 Skittles and you're pulling it from there. Okay. So no, this is not a binomial setting. Okay. If it doesn't satisfy one of these conditions, then it's going to be no.
What does the S stand for?
The same probability. Okay. All right. On number 2, it says find the probability of getting 5 green Skittles if this is not a binomial setting. So you got to think the first is green, then the second is green, and the third is green. We're going to show our work. So probability of all 5 green. All right, so we put our hand into the bin out of the 10,000 Skittles. If 20% of them are green, what's the number that's going to be on top?
Yeah.
2,000. All right, on the next one. And we're just pulling out 1 Skittle, correct? Say it again. There's 1,999 Skittles per chance. And let's say that we took out 1. Okay. On the next one, we're going to have 1,998. On the next one, we're going to have 9,998. And we're having 1 less each time of the 5 Skittles that we pulled. Okay. Okay, why are we multiplying and not adding? It's not an or. Okay. All right, so go and take a moment, plug it into your calculator, tell me what you get. Yep. And is times or is add.
Is that the starter's point?
It is. I've drank one every single day, Mo. Yes.
What it is, the great thing is just like the same thing.
Okay. So when you plug it into your calculator, it gives you 0.000319. You'll have a very small chance of all of those being 5 green Skittles. All right, let's think if this was a binomial setting. Find the probability of getting 5 green Skittles. Okay, so if it were a binomial setting, and we are finding the probability of all 5 being green, we would have 5 choose 5 multiplied by 0.20 raised to the 5th power times 0.80 raised to the 0 power. Yes, it is raised to the 0 power. Why is it raised to the 0 power? Because we don't want the failure to happen, right? Remember, in order to get the 5 choose 5, you're going to go to menu, you're going to go to probability, and you're going to go to combinations. You're going to type 5, 5, and then type out the rest of that equation. That's not right. You should have gotten this. Make sure that you can type this into your calculator. This unit is really hefty on your calculator. Yeah. Type in like the fractions. All of that. Yeah. Yeah. Yep. This one right here, yes. I think it is. Man, y'all satting up a bunch, but y'all keep it all blank. Really, really bugging me. Y'all want me to make y'all move to a seating chart? So then tell your friends, be quiet. You get on my nerves. Okay. All right. No, it's not. The only things that you're given on there is the mean and the standard deviation on the formula sheet. So that binomial formula, you got to know. Yeah. Okay. So how do your answers from 2 and 3 compare? How do your answers from 2 and 3 compare? Excuse me? They're extremely small numbers. What else? They're almost the same. They're almost the same. Okay. So why do we think that is? Well, the probabilities in 2 change so little because the sample is so small relative to the population. So we only pulled out one Skittle out of the total of 10,000 Skittles. We were only looking at one of those Skittles. So it was super tiny. It wasn't really impactful. Okay. Now, Mr. Wilcox now grabs a huge handful of 100 Skittles from the large bin of 10,000 Skittles. Let X represent the number of green Skittles. No, I'm just reading for my health. It's fine. X can be considered a binomial random variable because the 10% condition is satisfied. Okay, and we're going to talk about that in just a second. Okay. What is the probability of getting at most 11 green Skittles? Show your work. So we're going to use our calculator on this one because now we've got larger numbers. Okay. We want the probability of at most 11 Skittles. So we've got binomial CDF. Okay. What is our number of trials? The number of trials. How many Skittles are we pulling? 100. What's the probability of us getting? Okay. And what value are we looking for? 11. So when we plug that in, go ahead and take a moment, type that into your calculator. Practice typing it in. It doesn't get easy if you don't practice. All right, when you type it in, you should have gotten 0.0126. Okay, 0.0126. What is the approximate shape of this distribution? Look at the little graph down at the bottom. What does it look like? Okay, so approximately, because remember, we can't say absolute, approximately normal. Okay, go ahead and calculate the mean and the standard deviation for this one. Remember, for mean, we're taking n times p, and for standard deviation, we're doing the square root of np times 1 minus p. Take a moment, go ahead and find the mean and the standard deviation. So you're finding the mean and the standard deviation. So for mean, I got 20. For standard deviation, I got 4. So what you got? Okay. All right, so now we're going to redo number 5 using a normal distribution. Okay. How did we do that in, I think it was like chapter 2. Do we remember? If you were given a normal curve and you needed to find the area underneath the curve or the probability, what'd you do? If I throw this back in your atmosphere. Yeah. Okay. So what number are we looking for? 11. What was our mean? 20 divided by 4. That gives us negative 2.25, right? We go into our table and we find that probability. Then that means that our area is going to be 0.0122. Which is almost the same as what we got on number 5. Why is it different?
Because you remember.
Yep. Yes. Yes. So we need to talk about the 10% condition. Yeah. Okay. Because why does it matter? 10% condition means that the number of trials has to be 10% of the population. Okay, so here's our sample size. Sample is little n. Big N is population size. Has to be 10% of our population. So that's why on problems 2 and 3, we didn't use 10% of our population. Okay. Now the large count condition, another one that we got. Large counts condition. That means that N times P needs to be greater than 10. And N times 1 minus P has to be bigger than 10. So we can use a normal distribution to model a binomial distribution if these conditions are satisfied.
What? If it's satisfied, it can be like normal. So the reason they are doing this.
What did you just say?
I said, if these two conditions are satisfied, then you can use a normal distribution to model a binomial distribution. Normal curves, our mind makes sense of that. You already know normal curves, right? It's like, all right, flip the page. Yep.
Number 3, on the earlier ones, you can use the binomial PDF, right?
Getting exactly 5 Skittles. They get the same. Well, so that you can't use a binomial setting because it's not binomial. Up at the top, we've already determined that it's not binomial. Yeah. Yep. It has to fit the 10% condition and the large count condition. All right, so let's summarize. Okay, so you've got the 10% condition that we just talked about. And that's when taking a random sample without replacement. All right, so when taking a random sample without replacement, of size N from a population of size big N we can use a binomial distribution if N is less than or equal to 10% of the big N. Yeah, I'm wondering if I rewrote that. Okay. Then we talked about the large counts. That's another condition. We use a normal distribution. Use a normal distribution. A model a binomial if N times P is bigger than or equal to 10 and N times 1 minus P is bigger than or equal to 10.
So which is kind of against each other, since the 10% condition makes it if we can use binomial. And then the lifetime is we can use binomials for a normal. So then if both of them multiply, so if it's one or the other.
So if it's this, then you're using binomial. Large counts, we're using a normal. Okay. Go ahead and take a look at 1 through 4. Go ahead and take a look at 1 through 4. Do not just sit there and not try. Okay. Really quick, let's talk. For binomial distribution, remember we've got the acronym BINS. Okay, is it binary? Is there a success and a failure? Yes. Okay. So the success would be eating breakfast. And then failure would be not eating breakfast. Failure. Okay. Let's talk about the number of trials. How many people are we taking? 500. Okay. Is it the same probability for each student? Yes. So 0.65 is the probability. Let's talk about the independent. Is it independent? Okay, so it's not independent, but we satisfy the 10% condition. That's where the conditions help us out. So what is the 10% condition? What's our sample size? Out of how many people do we have? 10% of all high school students, right? Okay, all high school students in whatever state place this is.
How do we know how much that is?
Well, if I'm making a statement of 65% of high school students, who is that? Did we say specifically one school? We said all high school students, right? Okay, so is 500 less than 10% of all high school students? There's a lot of them, right? So it satisfies that condition. Okay, so it may not be independent, but it satisfies the 10% condition. Yes.
This without knowing what the condition is.
I mean, how many students are there in high school?
Even one school would be like, maybe, wait, no.
We're taking a sample that's smaller than 10% of all high school students. Can y'all stop? Why are we what? They didn't give us exact numbers. I mean, like, I could look up total number of high school students,
I feel like.
right?
Questions, like, well, it's definitely like, oh, well, no, if it's gonna be.
I mean, how many high school students do we have in Gwinnett County?
Not really.
So there's 180,000 students total in Gwinnett County system.
Yeah.
So of that, probably, let's just say like 20%. So what's 20% of 180? Okay, so is 500 less than 10% of that? Yes. And that's just talking about Gwinnett County. Yep.
I understand that. There's a sample of 500 in the population and 10% instead of saying that it is definitely like 100% that would that not fit against NYSERDA's because of the
I mean, you still, like, on here, you would say it's not independent, but it satisfies this condition. It's kind of like the exception to the rule.
So you I was kidding about it. Simply.
We're gonna do a FRQ on this. Like, we're gonna do a frappy practice. Okay? Yes. It's gotta be binary at the very least. It's gotta have the same probability each time. Okay, number 2, it should have been 0.0113. Number 3, it satisfies the large counts conditions. Okay. And then number 4, you would find the z-score, and then you would go in and find the probability, and then call it a day. And that probability would be 0.0095. Okay. And you're going to see that that's somewhat close to what's going on here. Somewhat close. Okay. All right. Tomorrow, we're going to do